All right, good morning. I started the recording. Yay! So you're all being recorded. Yeah, okay. All right, so we're doing lab number 12, which is the circular motion lab. We are doing this in lieu of a lab final, so you do not have a practical one here. We're just going to be doing this lab, and you're going to be turning it in, and this will be the last lab that you do. I would like you to put pictures of your journals up. I put a place online for you to put pictures of the journal, so if you could do that, that'd be great. All right, so
you want us to put our journal up sometime this week, or?
Yeah, please put it up sometime this week. That'd be nice. Just take pictures of what you have. I'm especially looking for the first half labs, which go up to lab number 6. If you've done stuff in your journals after the COVID hit, that's great. Yes?
Professor, I have a question. Is there like a sheet or something that says what should be like for each journal entry in there, like the notes from the board and like other stuff?
There was one. I gave it to you early on. But I don't want you to stuff, so just give me what you have. Okay?
Okay.
Yeah, because I'll know if you stuffed.
And for the data sheet, which pages do you want us to print out?
Okay, so you're only going to print out page number, let me see. Let me share it with you now. So now that I have it, let me share this. Okay, so you're only going to print, whoop, go back. You're only going to print out, wait a minute, what happened? Wait, this isn't right, is it? No, okay, I'm sorry. This has extra labs in it that you don't even need. Wait, what happened? Oh, this is weird. Okay, something happened. I'm not sure what happened. View. Let's do this. Okay. All right. So you're going to print out this page right here. And this should be 15. So you can change that 15. Am I able to edit this? No, it says protected view. I don't want protected view. Protected view. Oh, well, fine. This is going to be 15, not 10. Okay, that's going to be 15. All right. So going to be time for 15 revolutions, because notice down here it says T15. So yeah, so it's going to be time for 15. So you need to change that 10 to a 15.
Do we print out the second, the page right after that one?
No, you don't have to, because even though there will be questions, I'm going to change what the questions are. So yeah. So, all right, so let me briefly go over the circular motion theory. I'll do it on the board behind me. All right. Okay. So for today's lab, we're going to have a little device that we're going to use to rotate an object. The object we rotate around will be a cork. And we want to be careful with letters here, because we're going to label this cork mass little m. So the lowercase letter m is going to be the rotating mass. And then we're going to have it attached to a weight, capital letter M, down here. Okay, so capital letter M down there, lowercase letter m up. It's going to be our cork. All right, so then we're going to be rotating this in a circle of radius capital R. And Newton's law for the rotation motion says that the sum of the forces toward the center of any rotation motion is equal to the mass little m multiplied by the speed squared divided by the radius. The mass times the centripetal acceleration. So hopefully you've learned about this somewhat in your lecture class. Okay, so let's take care of this left side first here. The force toward the center in this case is being provided by what? Can anybody understand? Oh, type. You can type whatever you can type it too. You don't have to fill it in. So the force toward the center here is being provided by what? If I have a string, what kind of forces do we have in a string? So you can type it in chat, or somebody can say it. type of force.
Tension.
It's tension. So we want to calculate the tension in the string. Now we're doing this in such a way that this mass will stay in place as this thing rotates. So in other words, it's not going to be moving up or down, which means that the tension in the string is going to be equal to the weight of this mass. So how do I calculate the weight of anything? So the force of tension in this case is going to equal to weight. How do I calculate the weight of anything? Gee, I wonder what it should be. Gee. I wonder how you calculate the weight. mg. Oh, I wonder where you got that from. See? Get it? Gee. I wonder. Never mind. Fine. Okay. So anyway, that's our weight. All right. The other thing we need to do is calculate the speed. We need to calculate the speed of this. Now, unless we're using tracker, we're not going to be able to calculate the speed. That's not going to happen. So we kind of have to use a different method instead. And so we're going to go back to our old friend, the period. And as you may recall, that the period
Dylan, we only print the one sheet that he showed us.
yes, just that one sheet, is the time for one revolution, or the time for one cycle. Now, in this case, a cycle is a whole entire revolution, all the way around. That's one cycle. So the way we're going to do this, because that's going to go by really quick, we're going to use that same technique that we used before. We're going to time 15 of them. So this would be the time for 15 revolutions. The time for 15 revolutions. And so how would I calculate the period, capital T, from the time for 15? What would I need to do? You can type in chat. What do I do? There we go, divide by 15. Okay, I divide by 15. It's just that same technique that we've been using all along. And by the way, that would have been one of the things that you needed to do on the lab final. You'd be trying to find the time for several different motions, and you calculate the period, and you have to realize, oh, I don't need a theory. I just take the time divided by the number of things. There you go. That's it. So we divide by 15. There you go. All right, so now what we have to do is we have to figure out the speed. So the V here represents speed, not velocity. I know because there's no vector in that. There's no vector in that speed. So this is speed. So tell me what the definition of speed is. So now we're referencing speed. What's the definition of speed? Okay, let's see. I wish I had a wheel. Yes, it's distance over time. You solved it. Okay, there you go. All right, so it's distance over time. So in this case, you're going around a circle. So the distance traveled would be what? So you're going around a circle. What do we call the distance around the circle? What distance is around a circle?
Circumference.
It's the circumference. So the circumference is the distance. That's the distance. How do I calculate that for a circle? I'll give you a hint. There, it's got a pie in it. There's lots of pies in circles.
Is it
What
like
else?
2 pi r squared, something like that?
Close. It's just, it's not squared because it's a distance. So it's just 2 pi r. 2 pi r, that's it. Okay? So it's just 2 pi r. Okay? So now, what is the time for it to take to go around the circle? Well,
Period.
that's a period. We've defined that as a period. So what we can do is we can take this, plug this in here, and we take this as 2 pi r divided by capital T. So now what we do is we plug all of this up here into this equation. Okay? So I write this down. So capital M times G is equal to little m over r multiplied by 2 pi r divided by capital T squared. And what I do is I take this and I solve it for G. So I'm going to solve this thing for G. When I do, I get this. I get that G is equal to some constants here, 4 pi squared times little m divided by capital letter M multiplied by r divided by t squared. So now I'm going to show you what a lot of scientists love to do. First of all, we're going to set this thing up with this mass up there and this mass down here in a string. And we're going to vary this radius r, and we're going to see how the period t changes when we do that. But if I look at this equation for G here, notice that all of this stuff over here is the same for every radius. So I don't want to have to plug in every time 4 pi squared little m over capital M in my calculator every single time. So instead what we're going to do is we're going to calculate this number right here, and we're going to call this kappa. So we're going to say kappa, which is a constant, is 4 pi squared little m divided by capital M. I could have called that constant anything I wanted to. I wanted to name it something Greek so you would realize it's not really related to anything else we do. And also notice that when I calculate this kappa, the units here are going to cancel the units here. The units of lowercase m are going to cancel the units of capital case M, which means that this isn't going to have any units. And in fact, all we have to do is we could have our masses be any units we want to, as long as they're both the same, and it's going to be fine. Okay, well, now let's make ourselves the setup. So I'm going to pause the video part of this while we create the setup. So, because it takes a little bit, and if somebody's watching from home and they want to review me making this. All right, so push it back a little bit. So we're going to make our setup for this class. I'm going to go stop the recording.